So today I will continue the construction of some representation of infinite dimensional algebra on the moduli spaces. In the last week I talked about the Hilbert scheme points, but today at the beginning I'm considering its higher rank analog, which is called Giesecke space. These spaces are introduced by Sasha last week. Or maybe not precisely introduced, but very its cousin was preserved. So let's start. So let P2 to be a complex projective plane, and I decompose. It has a line at infinity. I denote it by L infinity, and the complement is affine plane A2. And I consider MRN. It's a modular space of framed torsion free shifts on P2. So E is a torsion free shift on P2, and phi is a framing. So framing is just a trivialization of the restriction of the torsion free shift at line at infinity. So this phi is a framing. And the two numbers R and N are positive non-negative integers. R is the rank of E, and I only consider R the case when R is positive, and C2, N is the second Chern class, so this is non-negative number. And it's known that this MRN is a smooth. In fact, it's known that this is a hyperkähler manifold, non-compact, but so its dimension is 2Rn, complex dimension is 2Rn. And if R equals 1, then this is the Hilbert scheme points, which I explained last week. So maybe if you don't know what is torsion free shift, then it's a kind of holomorphic vector bundle with mild singularities, and you don't need to worry so much about its properties. Basically, I just mentioned that this space of vector bundles form a space of those torsion free shifts form a nice space. That's the only property which I so far use. And later, I specialized to the case of Hilbert scheme of points. Then everything, I hope, it's just the ideal set. As a set, it is a set of ideals in polynomial rings. So that is something concrete. So I hope it's easy to understand. And in fact, what Sasha explained last week is more difficult, and the Uhlenbeck space, which I denote by U of N of SLR. So I consider Uhlenbeck space for the group SLR. So this space is more difficult, in fact, than Giesecke space. Why? Because there is a morphism map from MRN to this Giesecke space to Uhlenbeck space. And as I said, MRN is smooth, but the Uhlenbeck space has very complicated singularities. So this parameterizes some holomorphic vector bundles plus singularities, but because some informations are lost, this Giesecke space is larger, and this space has form a nice smooth space, but the Uhlenbeck space is singular. And MRN is hyperkähler, so in particular holomorphic symplectic. And this kind of homomorphism was constructed for more generally projective surface by Junli and Morgan. And also this resolution of singularity is very similar to what is called the Roman resolution of the K-psi maps. And but unfortunately, such nice resolution exists only for type A. So if you replace, if you consider Uhlenbeck space for more general group, then people expect there is no such nice resolution. I don't think there is such proof in general, but I'm sure that maybe it's not so difficult about not proof. And also for this, the case of K-psi maps, the Roman resolution can be defined for type A, but you count for other types. So this kind of nice resolution of singularity exists only for type A. But anyway, so because it's easier to deal with smooth space, I consider these spaces. And on this space, you have an action of R plus two-dimensional torus, two from the action on the plane. It extends to the projective spaces, projective plane, and it induces an action on the moduli spaces. And I also have an action of R-dimensional torus, which just you compose this phi, Fleming phi, with this element in the torus. So you have R plus two-dimensional torus acting on the space. Then the main player is its equivalent cohomology group, or by Poincare duality, its equivalent homology group. Or more precisely, this is what I call Borel-Moore equivalent cohomology group. So this is, so the notation is the same as the usual homology group, but I implicitly assume that this is this is defined by cycles of locally finite chains, not the finite chain. And I consider it's direct. I fix the rank R, and I consider all in second chunk class n simultaneously, and I consider direct sum. And since this is an equivalent cohomology, it is a module of equivalent cohomology of a point. So equivalent cohomology of a torus of a point is a polynomial ring. So you have two variables epsilon 1, epsilon 2 from the first two-dimensional torus factor, and A1 to AR are variables from the second torus factor. So I mentioned in the last lecture that for the usual cohomology group, things are rigid. There's no parameter. But if once you go to the equivalent cohomology, there's you can have a parameter. That is one good point. And that, but unfortunately, I cannot. I can't reveal. I can't study such deformation in this lecture. But in fact, I will explain the second advantage of considering equivalent cohomology. That is, I mean, more. In fact, equivalent cohomology is more difficult to compute, but equivalent cohomology is easier to calculate. In fact, that is the reason why. To studying equivalent cohomology of the variety is a good thing. So that feature I will explain later. So on this space, blackboard H, you have two natural operators acting on this. The first one, the second one is a familiar one, which the similar things I already introduced last week. The first one is more naive, and but I didn't explain at all in the last week. That is the operation or a multiplication of chunk class of some vector bundle, natural vector bundle on the modular space. And there's very natural vector bundle on this modular space. So if MRN, for MRN, the rank is n. And for rank R equal 1, so I define the Hilbert scheme of points as a set of ideals. And then you consider the quotient space. And by definition of the Hilbert scheme of points, this is n-dimensional vector space, if the number of points is n. So you vary this vary ideal that form a vector bundle over the Hilbert scheme. And you can play a similar game for the higher rank modular space. In theoretical rounding, that is, you first consider the so-called universal sheaf on the modular space, the product of modular space and the base space, and you will take a push forward. But anyway, so that is a very anyway standard construction of vector bundle, and you just imagine this is it's a kind of generalization of this. And then you can consider its Chern classes, and since cohomology group is a ring, you can consider multiplication of the Chern class as an operator on the cohomology group, or its direct sum. So this operator is, geometrically it's more natural operator, but it keeps the number of points n. So somehow it looks like more standard. Those are more standard operators. But it turns out in view of representation theory, this operator is more difficult than the second operator, in fact. So I will explain it later. And the second one is given by the correspondence. So you consider a pair of framed sheaves, and you have this kind of inclusion relation. And the framing are incompatible. So this is just a generalization of the correspondence, which I explained last week, from rank 1 to higher ranks. And in fact, in the last week, I not only just increase the number of points by 1, but I also consider increase much number of points. But that is, so I wrote here. So we can consider similar, like in rank 1 case, we can consider similar variety which increase the number of points by k instead of 1. But the space is not smooth, and it is much difficult to study, especially in this equivalent cohomology. That is still possible, but it's difficult, becomes difficult. So today I just consider the case when the number of points is increased by 1. And this space is very nice, so it's smooth, and the dimension is 2Rn plus R plus 1. That is just again, this is Lagrangian in appropriate symplectic variety. So instead of two product, as in if you remember the last week lecture, I added the C2 or X as in third factor, and you have this MRN. In fact, this is a subvariety in the triple product, because if you have E1, it's phi, then the first and the second is just E1 and E2. And then third factor is just E2. If you consider E2 divided by E1, or opposite, E1 divided by E2, then, so since this is, the Chern class differs only by 1, this is concentrated at a single point. So if you consider its support, this is a single point. So this is a subvariety in the triple product, and this is Lagrangian in the triple product. So by the philosophy of the quantization, so once you have the Lagrangian subvariety in symplectic manifold, then it gives an operator on the. It first gives a vector on the Hilbert space, quantum Hilbert space, and by changing one of factors by a Hilbert space by its dual, so this gives an operator on the Hilbert space. So this is very natural operator in this point of view. But the first operator is also natural in geometric point of view. So we want to study how they are related. One thing is that from this picture, by pull back and push forward, I can construct operator. But one of the factors is not one of the projection is not proper, so you must be a little bit careful. But in this case, when you increase the number of points, you must be slightly change the correspondence by imposing that this point is concentrated at a single point. So that is a technical matter, and you don't need to worry so much about it. So essentially, just pull back by first factor and projection into second half factor, and just operators in the opposite direction. Then the theorem, which was proved last year by Molecule Kung-Fu and Shifu and Baselo, is the following. So this, these operators, two types of operators, Chern class and this first Fourier mode of Heisenberg-like operators, gives a representation of the double algebra on the space H. And this construction is motivated by a conjecture by physicists, like Gaiotto and Tachikawa. So it's usually called AGT conjecture. So AGT conjecture gives some dictionary between the four-dimensional gauge theory and the two-dimensional conformal field theory, and that is this result is just iceberg, tip of iceberg in AGT conjecture. But anyway, so double algebra naturally appears in conformal field theory, and somehow this is a starting point of the full understanding of full mathematically rigorous understanding of AGT conjecture. And I don't make the statement is a little vague, but in fact it is much, you can make much more precise statement. But I don't want to do it. First of all, the definition of double algebra requires some time, and it's not. Unfortunately, it's not so simple. Heisenberg algebra is defined by single infinitely many generators and single relations. And maybe I should say so. When R equal to double algebra is Virasoro algebra, which you may heard about it. So that Virasoro algebra has infinitely many generators and one. Not in fact, it's infinitely many defining relations. But anyway, so you can write down the defining relation. But from GL3 and GL4, double algebra has no such presentation, and you must introduce some other way to define this algebra. And in fact, this is the so-called vertex algebra, and even the axiom of vertex algebra requires some things, and so anyway, I cannot do it in this one lecture. So I just present you some idea of the proof of this theorem, which still interesting, and which gives a first step towards the full proof of this result. So from now, I return back to the case of Hilbert scheme. And in this case, Virasoro algebra was constructed by Len after my work. And somehow the things which I will explain from now is another proof of a result by Len. And further, I assume epsilon 1 plus epsilon 2 equals 0, which just means instead of two-dimensional torus, which you have in the first factor in the full torus, I restrict it into the C star, which is hyperbolic in T2, namely one of the if one of the component is T, the other is its inverse. It makes many things very simple. And for example, this is nice because it preserves the holomorphic symplectic structure. So if G1, G2, or maybe xy, if xy is a coordinate on C2, so this T, I multiply Tx and T inverse y. So holomorphic symplectic form in this coordinate is dx wedge dy. So this is preserved. Then many things are simplified under this restriction. So you can do for the two-dimensional torus, but since I want to make many calculations to simplify it, so I assume this condition. So now from now I consider the R equal 1 case, and I enlarge the algebra of infinite dimensional Heisenberg action to action of Virasoro algebra. So any question?
Where ordinary Virasoro action?
Ordinary, what do you mean? So if you R equal to it's a little bit confusing point. So if R equal 1, double algebra is infinite dimensional Heisenberg algebra, and double R equal 2, it is a product of the Heisenberg infinite dimensional Heisenberg algebra and the Virasoro algebra. But this Virasoro algebra, which I will speak now, is different from this WGL2. Because I'm only consider R equal 1 case, but somehow it is very, very closely related. So, in fact, how to say? To show that the WGL2, the Virasoro algebra acts on two-dimensional cohomology of two-dimensional rank 2 sheaves, I need this result for R equal 1. So it already explains some feature of this theorem in that sense. And for in algebraic side, it is well known that if once you have an action of infinite dimensional Heisenberg algebra, then by the so-called Sugawara construction, or how do you say, maybe Fagan-Fuchs representation in more general context, you have an action of Virasoro algebra. There is some explicit construction. Once you have the Heisenberg construction, it automatically contains the action of Virasoro algebra. I will explain it later. So the goal of this my second goal of my this lecture is to explain this algebraic construction in a geometric way. That is my goal. And Len proved it by a geometric consideration, like which I explained briefly in my last lecture. But today I will take a more combinatorial approach. That is more, I think, more powerful, and somehow it shows the advantage of the use of equivalent cohomology group. And the equivalent cohomology group is related to closely to combinatorics, and so somehow, how to say, you can use various techniques in combinatorics to combine it with the study of equivalent cohomology group to get some powerful result. new ingredient is a study of fixed point of this sister action. By the way, so my torus is R equal 1 case. This is 2 torus times T of 1 because R equal 1. But this T1 acts trivially on M1n. In fact, it is also even for Rn, even general R. But so this action is trivial. So I forget this one. From now, I only consider the first part, and I then restrict to C star. So I'm only consider this C star action of the Hilbert scheme points. So in equivalent cohomology, it is very important to study the fixed point of this C star action on this space. So maybe if you heard about equivalent cohomology in some lecture, maybe you study the fixed point in of the C star on the Grassmannian, and then you can parameterize fixed point by certain partitions, and then it is somehow related to Schubert varieties, and you find lots of combinatorics. They are related to lots of combinatorics, and you have a similar story for Hilbert scheme points. So first of all, the C star fixed points are parameterized by partition again. So partition, the number of partition, I always consider it as a Young diagram, and I denote in this way. I think it's a French way, and English and Russian wrote writes Young diagram in different ways. But anyway, so this is my way, and number of boxes of this Young diagram is equal to n. And that gives me an ideal in this way. So I just write monomials, 1x and y and xy like this. Then I define the monomial ideal, I lambda, to be those span of ideals which is outside of this partition. Then because once this monomial is contained in the ideal, it's all the ideals in the left, right, and all the up are also contained is not contained in the Young diagram. That means that that is an ideal. So this rule gives an ideal, and it is spanned, since it is spanned by monomials, it is called monomial ideals, and it is clearly fixed by C star action because those monomials are multiplied by some scalar. And you can also study the tangent space of Hilbert scheme at the fixed point. Then, because it is a fixed point, it is a representation of C star. So you can compute the character, and its character is given by this formula. So it is so this space is 2n dimensional. So it is a sum of 2n terms, and you have some combinatorial expression which involves some natural which you find in combinatorics of partitions. That is the so-called hook length. So once you have a box S in Young diagram, then you can consider the so-called arm length and the leg length. So arm length is the number of boxes above the box, and the leg length is the number of legs, number of boxes which is right of these boxes. So my Young diagram is sleeping on the floor. So this is arm and this is leg, and hook length is the sum of arm length and the leg length plus 1. So it's just the number of hooks, number of boxes in this hook. Then this character of the sister tangent space is given by this formula. T to the power h lambda, hook length of the box S, and also minus negative of hook length. And since the number of boxes is equal to n, the total number of sum is equal to 2n. So this is 2n dimension. So this is, I mean, if you don't really familiar with this kind of algebraic geometry, how to compute the tangent space of Hilbert scheme at a point, it's a little bit difficult to derive this formula. But once you learn basics on Hilbert scheme point, then it's not so difficult to derive this formula. It's some standard knowledge for algebraic geometry. I just briefly mention how this kind of things happen, and basically only first part. So ideal in polynomial is generated by some elements that is just a polynomial. But so polynomial is a sum of monomials. And if you consider monomial x, so L. And if you consider the larger torus action, then things are more clear. So if you consider T1, T2, then this is multiplied by A, L, M times T1, L, T2, M. This is mapped to right? And if this, so suppose you have a monomial ideal I, which is fixed by this torus action, then you take this to be generator. Then if this is invariant of the torus action, this must be also in the ideal. But since these are different, these values are different for generic T1, T2, if L and M are different. So it means if this is also contained in the ideal for generic T1, T2, then somehow it must be, how to say, generator must be also, or well, maybe I don't explain well. So if this is also contained in here for any generic value of T1, T2, then each sum summand for L and M must be contained. Not only the sum. So for all T1, T2, then it implies that each term, XL, YM is also in, because they are different, and it becomes linearly independent. So if the ideal is invariant under this torus action, then it must be generated by those monomials. So it must be monomial ideals. And if you draw the monomial ideals, then you naturally get this Young diagram. So the statement is clear for this if you replace the system by larger torus action. And then you study the characters of the tangent space at a point, and you restrict it into C star. And then you find that no direction is fixed under, how to say. So if you have, so you consider tangent space. I already write xn, right? Instead of Cn, I write it. So this is a module of C star. And so if you have a fixed point locus, so F is a component of the fixed point, then its tangent direction containing I lambda. This is just the way to zero space in tangent space. Then once you compute the character, then just you compute the character for the larger two-dimensional torus action. Then you just check that there is no such way to zero space except 0. So then you show that this F must be zero-dimensional. Then it just means that this F is nothing but the consists of a single point I lambda. So in that way, so there's unfortunately no direct geometric proof for it. But anyway, so again, this fixed point is still parameterized by Young diagrams. And the tangent space is given just compute by restriction. So it uses some knowledge of algebraic geometry. It's a kind of cohomology, so it's really standard object in algebraic geometry. Then I consider the Euler class of this tangent space at I denote T lambda of xn instead of Ti lambda of xn. The Euler class of the equivalent Euler class of the tangent space is just a product of all weights. So because the formula was T to the power h lambda of s plus T to the minus of h lambda of s. So you get this formula. Minus 1 to the n. Epsilon is just the second cohomology group of the equivalent cohomology point. And so T corresponds 1 epsilon. If you raise the power by h lambda s, then you multiply by h lambda s. So you naturally get to this product of hook length, which I denote by h lambda. And this h lambda is a object which you find in literature in combinatorics, and it naturally appears in. So this kind of Young diagram is related to representation theory of the symmetric group, and such kind of combinatorial structure naturally appears. Then it is natural to consider the class homology equivalent to cohomology class, but you also divide by this kind of expression. So you need to. So this is a polynomial ring. This is modulo of a polynomial ring, but I instead enlarge the scala from polynomial to rational functions because I divide by epsilon to the power n. So I just pick up somehow half of weights and ignore the sign, and I multiply epsilon n to times h lambda, and I multiply by the Poincare dual of the class represented by a fixed point. So this is a modified fixed point class. Then Then this class, if you consider the integral of this class, it is up to sign, it is equal to 1. So in that sense, so this is a orthonormal. This gives an orthonormal basis of the equivalent cohomology. So this is a very nice basis. So S lambda So I want to compute the first of all, so if I compute the integral of two different points, two different fixed points in Hilbert scheme, then this is obviously 0 because those are lived in the different points. They are separated. So the only non-trivial thing is so if you compute the intersection of two points naively, then because any 2 points can be moved on the space freely. So even if I mean, to compute this kind of intersection pairing, you can usually you can first move those homology class to generic point, in general position, and then compute the intersection. So since these are point class, so if you can move to generic position, then it obviously the intersection is 0. But in the equivalent cohomology, you cannot move those 2 points into general position in an equivalent manner. So the computation is more subtle. And this computation is given by the fixed point formula. So this is more general result, which I hope most of you know. So if you have a manifold, complex, this you just as a complex manifold. So for simplicity, I first assume this is compact. And suppose you have a sister action. And suppose you have a equivalent cohomology class. Then the integration of equivalent cohomology class over the manifold is and suppose M of C star. This is just isolated finite points, like in this case. Then you, instead of make integration over the space, it can be expressed by a finite sum. So this is the famous Atiyah-Bott fixed point formula. Or maybe many people reference Bernoulli-Beron. So this is, you first consider, it is a sum over fixed point. and you restrict the cohomology class to a fixed point. This is you put in the numerator, and in the denominator you put equivalent Euler class of the fixed point. So this is the famous fixed point formula. So have you ever heard about this formula before? I mean, this is how to say. So some verse. Well, this is a kind of big generalization of integration by parts. So integration by parts means that instead of integrating sums over interval, you just evaluate at the end of the interval. So instead of integrating over the space, you just so this fixed point is something analog of the how to say analog of the boundary of edges, boundary of intervals. But because the space is higher dimensional, so you must correct by this kind of Euler factor. This is very useful and.
It was explained by Losif in his lectures.
Oh, really?
He was discussing localization.
Localization.
Losif kind of explained.
Okay. Well, but I mean, I think it's of course it is important to know the proof, but it is also important to know how to use it, because usually if you apply this formula in various nice spaces, then you usually get some combinatorial object which also occurs in different contexts. So it's really important. For example, if you take M to be Grassmannian projective space, then even for this, you still get something interesting expression. For example, if in this formula, if degree of alpha is not the dimension of M, then left-hand side vanish. That is clear from the definition of integration. But in the right-hand side, that is not clear. So in particular, it means if you apply this formula for when alpha is different, the degree of alpha is different from dimension M, then 0 equals some very, very complicated expression. So that is a very non-trivial combinatorial identity. Well, sometimes you can prove it in purely combinatorial way, but sometimes not. So this kind of play of the fixed point formula is quite interesting. But anyway, I use this formula. Then from my construction, so S lambda restricted to I mu. So this survives only on this is 0 unless lambda equal mu. So it is just a single sum. By the way, I need to explain this. If this is expression is, I assume this to be compact. Otherwise, the left-hand side needs care. But if this is true, so this then this is you don't need this assumption if you replace this by. Then the left-hand side may not be. You must be a bit careful what the left-hand side really means. But anyway, yeah, I don't want to this so much. So you just imagine that after some modification, this is true. Even this is left-hand side doesn't make sense even if M is not compact. So anyway, so I formally use this right-hand side as a definition of the left-hand side here. Then I divide by 0. Then because S lambda is half of the equivalent of Laplace of point. So you multiply two such terms, and then this it cancels with the denominator up to sign. And if you multiply this sign, then you get 1. So this class S lambda is also normal basis of this homology class. Yeah, I think I forgot to explain one thing in the last time. So I construct the representation of infinite dimensional Heisenberg algebra on the cohomology. But there is one standard construction of the representation of the Heisenberg algebra. Maybe I forget the cohomology class, I just consider. Or maybe it's more easy to consider the just one-dimensional case. So there is no. So this is a Heisenberg one-dimensional Heisenberg algebra. And Heisenberg algebra doesn't have a finite dimensional representation because trace of commutators equal to is always 0, but 1 acts by this. So it means the dimension of the space must be 0 because of this right-hand side. So you must have infinite dimensional representation. And there's very simple realization of this Heisenberg algebra on infinite dimensional space on polynomial in one variable. So this is called Fock representation. So this, in this, P is just the differentiation, and Q is multiplication. So this commutation relation is just differentiating the x by this ddx, and you get the 1. And on this, you introduce infinitely many x variables, x1, x2. And consider polynomial in infinitely many variables. It is also called Fock space. And the pk, for k is positive. This is annihilation operator, and this is because of this notation. I must multiply by k. And the pk for k is negative. It's just multiplication. But in fact, it is more natural to relate to this space instead of polynomial in infinitely many variables. It is more natural to relate symmetric polynomials. So this Fock space F. So symmetric polynomials well, so first of all, so you must define it in appropriate way. So this is you consider symmetric polynomial ring in n variables, and this is just some limit. You must take appropriate sense the limit in appropriate sense. So you increase n, the number n, to infinity. That can be done. For example, you can find it in McDonald's book. But anyway, I hope you all know that the ring of symmetric polynomials is generated by is a polynomial ring in elementary symmetric functions, or it is also isomorphic to power sum symmetric functions. So as a polynomial ring, as an abstract polynomial, so you can consider this as a either this or this. Again, so it's also this. Again, is also. But if you relate all these things to combinatorics, it's more natural to view this ring of infinite, the ring of polynomial ring of infinitely many variables as this symmetric polynomial in infinitely many variables. So then you ask that. So I want to. So eventually, this space is a representation, Fock representation of the Heisenberg algebra. So it should be identified with ring of symmetric polynomials. I extend the scalar, and I want to. I have this orthogonal basis for this space. So I ask that there is. I ask. I identify those two spaces by sending this orthonormal basis to a very standard orthonormal basis in symmetric polynomials, which is shear function. So shear, it is well known that the shear function is also orthonormal basis of the symmetric polynomials with respect to standard inner product. So by this way, I can construct an isomorphism of vector space with preserving inner product, like this. So my next goal is that first I realize. So I already have a Heisenberg algebra action on this space, and since this is usually I think it's better to consider this ring of power sum, if it's polynomial ring in power sums, then these operators, pk is multiplication by power sum or differentiation by power sum. So this is a vector space isomorphism. But next I want to identify this isomorphism, preserve the Heisenberg algebra action on here, which I constructed last week, and also those multiplication or differential operator by power sums. So to do it, I consider that this first operator is more difficult, and I consider the second operator given by this pullback and push forward. So this can be this again can be computed by studying the fixed point set in this middle variety. So xn and this is n. So you have two projections. And I mentioned that this is smooth if I increase only number of points by 1, and if I increase more, the space is singular. So you can study the fixed point set on here even if this is singular, but tangent space of the singular space doesn't behave well. In particular, the fixed point which I just write down here, which I just erased, doesn't hold when the variety is singular. So that's the reason why I stick to the case when the number of points increase by 1. Then I just study the fixed point set, the tangent space at fixed point. First of all, fixed point is so this is contained in xn cross xn plus 1, and also so I wrote that there's one extra factor, and you have C star action, and if it is contain, then each factor must be fixed. And for the last factor, there's only 0. 0 is fixed, so you can forget about it. So you have pairs of fixed point set in here and here. So both are, as I explained, both correspond to Young diagrams. So I have a Young diagram lambda 1 and so fixed point. Both are Young diagrams. So then I need to also impose the condition on lambda 1 and lambda 2, which guarantees that that is contained in this space. And this space is defined by pair of I1, I2, that the condition is ideal is contained in the other. One ideal is contained in the other. So it means you have two Young diagrams, which one is contained in the second. So this is the condition. So I have two Young diagrams, but I just draw I draw one Young diagram and draw another box, which is, so the number of total number of boxes differs only by 1. So the larger Young diagram is obtained by adding one box to the smaller Young diagram. So I just denote single box which you add to a smaller diagram. So this is a picture. And you compute the tangent space again. That is not so difficult if you learn algebraic geometry or how to compute the cohomology group. And that is given by this formula. T plus T inverse and some expression. But it involves both leg length and arm length for Young diagram lambda 1 and lambda 2. Both lambda 1 and lambda 2 appears. Well, lambda 1 and lambda 2 are different only on these boxes. So those leg lengths and arm lengths are almost equal, but not completely equal. There is some slight change, slight difference. And you compute the Euler class of the equivalent Euler class of the tangent space. That is the product of all weights. Then you find final answer is given in, maybe this is a typo. This is h of lambda 1 and h lambda 2. The final answer depends only on the hook length of lambda 1, the hook length of lambda 2. So here, it depends on arm length and leg length for lambda 1 and lambda 2. So this corollary is not so obvious, but it involves some interesting combinatorics. I think you can check it. So I don't give I don't explain the detail, but you somehow by calculating carefully enough how young hook lengths and arm lengths are different for lambda 1 and lambda 2, then the final answer, somehow miraculously, you just get product of hook lengths for the Young diagram lambda 1 and lambda 2. Oops. So anyway, this is the final formula for this. Then using this, you can compute the operator. Pull back and push forward. The computation is again application of this Atiyah-Boot fixed point formula. you so P, which with which? P2 star, P1 star. So S lambda is I lambda 1 divided by somehow half of. So I just ignore those epsilons and epsilon signs. So when I first pull back, this is the homology class. So I must replace this by cohomology class. Then I pull back. Then when I goes to pull back to cohomology group by Poincare duality, I multiply this by. So anyway, so this is. I multiply the tangent class for Euler class of tangent space at a point, and how should I write the class of fixed point. So on here, I have fixed point I lambda, and I have. So this is a single point, and I have I mu. So this is I have mu, and mu contains lambda. So you have lambda is fixed, but you have various choice for mu. So this mu is maybe this is lambda 1, this is lambda 2. You can box to several places. So then I have finitely many points, pair of I lambda 1. So I pull back to so this is the finitely many points. So I just consider the cohomology class just as a number, and then that is given just by P2 star of I multiply Euler class of T of I lambda 1 of xn to this 1. But divided by h lambda 1. But this is up to sign, this is h. And if I forget the epsilon, then this is square of h lambda 1. So one factor cancels. So that is just given by this. Then I put. So this is a Poincare dual. First, so this is Poincare dual. And then I put back to a pair. So first I consider it's a number on here, and I put back. So the number is preserved in here. Then I project to the second factor. So then I get to the sum over these partitions, which contains lambda 1. But here, when I multiply as a difference between this diagram and this diagram, I need to divide by the tangent, Euler class of tangent bundle to that value submanifold when I take the pushword in here. So that is a factor h lambda 1, h lambda 2, which I put in here. Then, so you get h lambda 1, h lambda 2. You still have h lambda 1 here. And I have this cancellation. And I then get this h lambda 2 over the h lambda 2 over I of lambda 2. So then this is just by my definition up to sign, this is S of lambda, symmetric shear function for lambda 2. So by the final formula is this one. So this is equal up to sign. This is sum of lambda 2 containing lambda 1 of S of lambda 2. And this combinatorial expression appears in symmetric function, in the theory of symmetric function. That is a Peiré formula. So if you multiply shear function by first elementary symmetric function or first power sum, it's just x1 plus x2 plus da da da. So Peiré formula is known for any symmetric function, but this is the Peiré formula. So if you multiply this elementary symmetric function to shear functions, you get to this formula. So in general, you have what I forget what you call, so n strips or some horizontal strips or vertical strips, or it depends on which you multiply to symmetric shear functions, elementary symmetric function or complete symmetric function. But for the first one, it's the same, and you have this Peiré formula. And our operator is exactly the same as the Peiré formula of the sign. So that means that this operator is given by the multiplication of E1 or P1. So in particular, it means under this isomorphism preserving vector space isomorphism preserving inner product, the Heisenberg operator in the geometric construction corresponds to this another Heisenberg algebra action or in the algebraic side. So this is the first one. This is the second type of operators. And then I consider the first type of operators that is given by the Chern class of vector bundles. So I only consider the first Chern class of the of natural vector bundle of the space. Then this fiber. So I define this vector bundle by the fiber of the a point ideal I is just given by Cxy of y. So I consider its first Chern class. Then this is again easy to get the combinatorial formula. So this I again write down the monomials into Young diagrams. And this one is preserved, and xy, because x is multiplied by t, and y is multiplied by t inverse. So xy is also preserved. So this is in this language, this is weight 0, and this x and also x square y. So this direction is weight equal 1, and this direction is weight equal to -1. And this combinatorics also appears in the literature, and it is called content of a box in the Young diagram. And again, it has some meaning in representation theory of symmetric groups. So if you have a box S in the Young diagram, then its weight is equal to CS. This is content of S. So you just measure the difference, distance from the main diagram up to side. Then the first chunk class of this vector bundle at the fixed point set is just the sum of all contents. That has some combinatorial meaning, so maybe you just forget. It is anyway the sum of content. So this operation and it's also clear that this S lambda is an eigenvector for this multiplication. So this is a multiple of S lambda, and you don't have any extra, how to say, you cannot have S mu because these S mu and S lambda are different points. You don't have such terms, so this is eigenvector. So this is a distinguished property that you have a. So this operator, its geometric meaning is clear, but you don't know in what its meaning in algebraic side. But you just ask that is there any operator acting on the space of symmetric functions such that those shear function is eigenvector and its eigenvalue is given by this sum of content. And in fact, such thing is not so much well known, but the answer is somehow you can look for very carefully. You can find it in the literature. So that is called I forget the name. So Gulden operator. So we conclude that the C1 multiplication, this is Gulden operator. So Gulden operator is just some cubic. I changed the notation from PK to alpha. So P alpha n is just a PL. It is coupled with either one or this one Carré dual of C2 or one Carré dual of point, according to whether it is annihilation or creation operator. So anyway, it is cubic in Heisenberg operator. So in some sense that is how to say, in algebraic side it is really complicated because this is cubic, so it's complicated operator. So anyway, you get this kind of cubic expression, and the sum total. So you have Fourier modes, and sum of Fourier mode is equal to 0, and one. So that's one of the factor is negative. One of Fourier mode is negative, or 2 among 3 are negative. That's only possible, and you have 2 such terms, but basically it is the sum of all cubic terms whose sum of Fourier mode is equal to 0. I think that's clear. And you just divide by 2. And it has some representation, meaning in representation theory of symmetric group. Then this is close to Virasoro algebra because so if you consider G, commutator of G and pk, maybe I switch to alpha k, alpha n, and you divide by n. Then, since this is cubic, so this commutator, if you take commutator with a single Heisenberg algebra, you get the quadratic in Heisenberg generators. So you just compute the commutator for this. I don't write down the explicit formula, but it's easy. Heisenberg generators. And this is exactly the Virasoro generator. In the Sugawara construction. Or Fagan-Fuchs. So you can compute. I mean, it's a little bit messy computation if you really don't know how to compute such kind of. So it contains infinite sum, so it's a little bit complicated. And the most appropriate language is the vertex operator or operator product expansion is most economical way to compute such kind of things. But anyway, for this case, I think you can really compute the commutation relation for this by without knowing any information. And you just take this cubic expression, which depending on n, is satisfied this Virasoro relation, Lm and n equals m minus Lm n plus this central extension term. So in this way, you get Virasoro algebra. Or maybe you may say that somehow this G is a more fundamental object because all Virasoro generator can be derived of one single expression. So anyway, this you can prove in a combinatorial way, and you recover the construction more and in a somehow a little bit more combinatorial way. So this is the end of my talk, and thank you for attention.
Thank you very much for a beautiful lecture.